Latch-Up and its prevention. Latch-Up is defined as a generation of a low-impedance path in CMOS chips between the power supply rail and the ground rail due to the interaction of parasitic PNP and NPN bipolar transistor. These BJTs form a silicon control rectifier SCR with positive feedback and virtually short circuit the power rail to ground, thus causing excessive current flows and even permanent device damage. Although the use of an epitaxial layer and the other process improvements have lessened the severity of latch-up problems, the reliability concerns persist on latch-up, especially in I/O circuits, since its package density also increases with decreasing feature sizes and spacing. The latch-up subsequently is inversely proportional to the product of the substrate doping level and the square of the spacing. In other words, if the spacing is reduced by half and the substrate doping is increased by 2 times, then the latch-up susceptibility would increase by a factor of 2. Figure shows cross-sectional view of a CMOS circuit with identification of parasitic NPN and PNP bipolar transistors in the equivalent circuit. Q1 is a vertical double emitter PNP transistor whose base is found by the anvil and its base to retro current gain beta 1 is as high as here you can see the figure A cross-sectional view of a CMOS inverter with parasitic bipolar transistor. B circuit model for SCR form of parasitic BJTs. It is several hundred. Q2 is a lateral double emitter NPN transistor with its base formed by P-type substrate. The base to collector current beta 2 of this lateral transistor may range from a few tens to tens. Anvil represents the parasitic resistance in the anvil structure with its value ranging from 1 kilo ohms to 20 kilo ohms. The substrate resistance also strongly depends on the substrate structure, whether it is a simple P- or P- epitaxial layer grown on top of the P+ substrate, which acts as a ground plane. In the former case, P sub can be as high as several hundred ohms, whereas in the latter case, the resistance can be as low as few ohms. To examine the latch-up event, first assume the parasitic resistances R well and R sub are sufficiently large so that they can be neglected open circuit unless the SCR is triggered by an epitaxial disturbance. The collector currents of both transistors consist of reverse leakage currents of the collector base junctions, and therefore their current gains are very low. If the collector current of one of the transistors is temporarily increased by an external disturbance, however, the resulting feedback loop causes this current perturbation to be multiplied by beta 1 into beta 2. This event is called the triggering of the SCR. Once triggered, each transistor drives the other transistor with positive feedback, eventually creating and sustaining a low impedance path between the power and the ground rails, resulting in a latch-up. It can be seen that if the condition beta 1 into beta 2 is greater than or equal to 1 is satisfied, both transistors will continue to conduct high saturation current even after triggering. Perturbation is no longer available. This latch-up condition can also be written in terms of collector, emitter, current gain, and also alpha 1 by 1 minus alpha 1 into alpha 2 by 1 minus alpha 2 greater than equal to 1 implies alpha 1 plus alpha 2 greater than equal to 1. Figure shows the IV characteristics of a typical SCR. At the onset of latch-up, the voltage drop across SCR becomes VH equal to VBE 1 sat plus VCE 2 sat equal to VBE 2 sat plus VCE 1 sat, where VH is called the holding voltage. The low impedance state is sustained as long as the current through SCR is greater than 1 is greater than IH, the holding current value, which is determined by device structure. As also note, the slope of IV curve is determined by the total parasitic resistance in the current path RT. Here you can see the figure current voltage characteristics of a typical SCR. Some of the causes for latch-up are screwing of VDD during the initial start up can cause enough displacement currents due to the well junction capacitance in the substrate and the well. If the screw rate is large enough, the latch-up can be induced, but if SCR can have a dynamic recovery before latch-up, when the screw rate is not very high, large currents in the parasitic SCR and CMOS chips can occur when the input or output signal swings either far beyond the VDD level or far below the VSS ground level, thus injecting a triggering current. Such disturbance can happen due to the impedance mismatches in transmission lines of the high-speed currents of the high-speed circuits. ESD stress can also cause latch-up by the injection of minority carriers from the clamping device in the protection circuit into either the substrate or the well. Sudden transients in power or ground buses due to the simultaneous switching of many drivers may turn on a BGT in SCR. In SCR, leakage currents in well junction can cause enough lateral currents radiation due to S-rays, cosmic rays, or alpha particles can generate enough electron hole pairs in both the substrate and well regions, and thus trigger the SCR and thus trigger the SCR in the following. We derive an expression for the SCR holding current IH in terms of current gains in parasitic transistor Q1 and Q2 for simple illustration. The circuit in figure B is redrawn in figure with important circuit parameters. It can be observed that I equal to I1 plus IRW, I equal to I2 plus IRS. Here you can see the figure equivalent circuit model for the SCR. From the collector emitter current gain alpha relation of Q1 and Q2, IC1 equal to alpha 1, I1 is equal to alpha 1 not IC2 equal to alpha 2, I2 equal to alpha 2 not I, and alpha 1 not and alpha 2 not denote the equivalent collector to emitter current gains, absorbing the effects of parasitic resistances into resistors. Thus, when alpha 1 naught and alpha 2 naught are used, the resistors in figure are effectively open circuited. Thus, the SCR current I can be expressed by I is equals to IC1 plus IC2 plus IC ICB01 plus ICB02, where ICB01 and ICB02 represent the collector-based junction leakage currents which can be combined into a single term ICB0. Combining equation through equation, we obtain following relationship: I equal to ICB0 minus IRS alpha 1 plus IRW alpha 2 by 1 plus alpha 1 plus alpha 2. The holding current IH is defined as the current with 0 IB0, that is IH equal to IRS alpha 1 plus IRW alpha 2 by alpha 1 plus alpha 2 minus 1. Now it is clear that when the sum now it is clear that when the sum of the collector to emitter gains of Q1 and Q2 is close to unity, the value of the holding current will be large. Thus, it is important to keep the gains of parasitic BJTs low. The parasitic resistances R sub and R well also play an important role in latch-up, since their currents actually reduce the base currents of the parasitic transistors and thus weaken the feedback loop, which leads to latch-up. Therefore, reducing these resistances may prevent latch-up. Consider the SCR current at the onset of latch-up. I is greater than equal to IH is equal to VD minus VH by RT when both transistors are at the saturation boundary, and hence the holding voltage is VH is equal to VB with VB1 equal to VB2 equal to VB. So here the SCR is modeled by the ADC voltage source of magnitude VH in series with resistor RT, combining the SCR current expression with expression equation with the equation using IRW is equal to IBE by R well and IRS equal to IBE by R sub. In equation we obtain alpha 1 plus alpha 2 greater than equal to 1 plus RT by R well alpha 1 plus RT by R sub alpha 2 by VDD by VBE minus 2 as the condition for the occurrence of latch-up in the presence of parasitic resistances. Compare this equation in simple latch-up condition. Given an equation, the extra term on the right hand side of dictates that the sum of the two currents gains must be larger than unity by that amount in order to satisfy the latch-up condition. And here you can see the figure CMOS inverter circuit in the latch-up simulation example. To trigger the SCR, therefore to avoid the latch-up, the extra term should be made as large as possible, that is resistance R sub and R one should be reduced as much as possible. The following simulation example figure illustrates the latch-up in CMOS inverters. Figure inverter structure shown in figure, which is triggered by pulse at the output node of the circuit. Guidelines for avoiding latch-up: reduce the gains of BJTs by lowering the minority carrier lifetime through gold doping of the substrate, but without causing excessive leakage currents, or reducing the minority carrier injection efficiency of BJT emitters by using stocky source drain contacts. Here you can see the figure simulated A voltage and B current waveforms of CMOS inverter circuit during latch-up triggered through the output node or through the output node. Use P-plus guard band rings connected to ground around NMOS transistors and N-plus guard rings connected to VDD around P around PMOS transistors to reduce RW and R-sub to capture injected minority carriers before they reach the base of the parasitic BJTs. Parasitic BJTs place substrate and well contacts as close as possible to the source connections of MOS transistors to reduce values of W and of the RW and R-sub. Use minimum area P-wells in case of twin tub technology and n-type substrate so that the P-well photoconnect can be minimized during the transient pulses. Source diffusion regions of PMOS transistors should be placed so that they lie along the equipotential lines when the current flow between VDD and P wells in some N-well I/O circuits. Wells are eliminated by using only NMOS transistors. Here you can see the figure I/O cell layout with latch-up guidelines. Avoid forward biasing source drain junctions so as not to inject high currents. The use of highly doped epitaxial layer on the top of heavily doped substrate has the effect of shunting lateral currents from the vertical transistor through the low resistance substrate layout. N and P channel transistors such that all NMOS transistors are placed close to VSS and PMOS transistors are close to VDD. Rails also maintain sufficient spacing between PMOS and NMOS transistors for prevention of latch-up. Chip manufacturers typically specify limiting operating conditions. As an example, Mikkel's Autel's interface device MD74SC550AC requires 1.9 volts over VDD and 200 milliamperes and 1.0 volts below VSS and 90 milliamperes to trigger out latch-up and I/O cell layout, which is designed using some of the latch-up guidelines listed here is shown in figure, where the same types of transistors are placed side by side. Thank you.